Welcome to Science Made Easy channel. A channel you will not want to miss. Topic.
So thank you and welcome to this video today. So in the last video we talked about how we can combine two elements together to form a compound. So today we'll be moving further from where we stopped, and all our requests have been heard and all our requests will be attended to. Some of us said that we should show a video on balancing of redox reaction. We show the video. And some of us also said that okay, we should show a video on, we should be posting videos on JAMB syllabus, and those ones to be attended to. But just give us some time, everything will be attended to. So thank you so much, we are really working on it. And thank you so much for your advice and for your support. So today, we'll be talking about how to get the relative atomic mass of an element, the relative molecular mass of a compound, percentage by mass, empirical formula. We'll be talking about all those ones today. And if time permits us, if our time does not go, we'll be also talking about chemical changes and physical changes. So thank you for watching this video. So let's talk about the relative atomic mass. So what do we mean by relative atomic mass? Normally, you should know that relative atomic mass is like a mass of an atom. So it's different from, we still talk about relative molecular mass. That one is for a molecule. But a relative atomic mass is for an atom. That means the mass that each atom carries. So how do we now define it? Relative atomic mass is the number of times the average mass of one atom of the element is heavier than 1/12 of carbon-12. So it's the number of times the average mass of an atom, of an element, is heavier than 1/12 of carbon-12. So normally, what do we usually use to measure relative atomic mass? There is no one way of getting the relative atomic mass of an element. There's no one way. Some says, okay, if you times the atomic number times 2, you get the relative atomic mass. Not for all elements. Even for there are some elements that their relative atomic mass is not times 2 of the atomic numbers. So normally you have an instrument for measuring the relative atomic mass, and the name of the instrument is mass spectrometer. Mass spectrometer. So this mass spectrometer can be used to measure the relative atomic mass of an element, and there's a lot of factors that determine the relative atomic mass of an element. When we start moving deep into chemistry, we still will know more about that. Talking about the isotopes, there are some elements that what determines their relative atomic mass is the isotopes. For example, chlorine. What determines the relative atomic mass of chlorine is isotopes and some other elements like that. But let us know the relative atomic mass of at least the first 20 elements. I train my students to know the relative atomic mass of the first 20 elements offhand, because that is one of the things that you have to do in chemistry. Don't say that, okay, when I do exam, they will give me the value. There are some times that you might not be given and you will need it. So we have to know the relative atomic mass offhand. So let's look at the first 20 elements and their relative atomic mass. We have what? Hydrogen. I told you that this is the what? This is the atomic number in the last class. The atomic number is the what? The number that belongs to in the periodic table. So we also have the mass number on the relative atomic mass. The relative atomic mass of hydrogen now. The atomic number is 1. The relative atomic mass is also 1. Helium. The atomic number is 2. The relative atomic number is 4. You can see times 2 for helium, but not for all elements. For example, number 3, lithium. The mass number is 7. That you can see. We have 3, 7. It's not times 2 here. So that means that I told you that for some elements it's not times 2. let's also write beryllium. Number 4, beryllium. So the atomic number of beryllium is 4, but the relative atomic mass is 9. You can see it's not also times 2 for beryllium. Number 5, boron. The mass number is 11. The relative atomic mass is 11. So many times, what's from the relative atomic mass is what? Is the proton number plus the neutron number. Is the proton number plus the neutron number. So sometimes we actually call this relative atomic mass the molar mass. That means what's molar mass? Molar mass is what? Or mass number. So now, for number 6 now, we have what? Carbon. The relative atomic mass of carbon is 12. You can see for carbon is just times 2. So it's still part of what we are talking about. For next one is nitrogen. The relative atomic mass of nitrogen is, for nitrogen is 14. Number 8, oxygen is 16. Number 9, fluorine is 19. And number 10, neon is 20. So you can see that you can follow times 2 for everyone, for all of them. So there are some that follow times 2, and there are some that are not times 2. So that is the relative atomic mass. So let's move from number 11 to number 20. So number 11 now. The next element is sodium. And the mass number of sodium is 23. The relative atomic mass is 23. For magnesium, the relative atomic mass is 24. For aluminium, the relative atomic mass is 27. For silicon, is 28. For phosphorus is 31. For sulfur is 32. For chlorine is 35.5. So I've told you before, the reason why the relative atomic mass of chlorine has 35.5 is because of the isotopes. We will still talk about isotopes later when we move further in chemistry. It's because of the isotopes. That is why the relative atomic mass of chlorine is 35.5. I've seen that question too in an external exam like WAEC before. State the reason why the relative atomic mass of chlorine is 35.5. The reason is just because of the word isotopes. Now, number 18, argon, which is 40. Number 19, potassium, which is 39. And number 20 is calcium, which is also 40. All these ones are the what? Relative atomic mass of the first 20 elements. Although many of them have decimal points, talking about 0.00. What I just do in writing them like this is approximate. I approximate them to a whole number. Except chlorine is one that cannot be approximated because the something of chlorine is 35.45, something like that. And if you want to approximate it, you can't approximate it as 35. It's wrong. Because this 5 at the back is up to, the number at the back of this 4 is up to 5. So we have said that okay, it's 35.5 rather than approximately to 26 or 25. So that is why the relative atomic mass of chlorine I can't just approximate to 36. So this is the standard, like normal relative atomic mass we use for them. So once you know this, we can now move to a molecule. What do we call a molecule? A molecule is the smallest particle of a substance that can exist alone. that can stand the load. What do I mean by that? I want to explain what I mean by that. Let me first talk about atom. What is an atom? Atom is the smallest particle of an element that can take part in the chemical reaction. It is the smallest particle of an element that can take part in what? A chemical reaction. That is the smallest way you can write an element. The simplest way you can write an element is also called what? Atom. For example, the simplest way I can write hydrogen is H. That is an atom of hydrogen, H. The simplest way I can write, let's say bromine, is Br. That is the simplest way. That is the simplest way I can write it. The simplest way I can write oxygen is O. That is the simplest way I can write it. And those are what we call what? An atom. So atom is the simplest or the smallest particle of an element that can take part in what? The chemical reaction. So I also have what we call the molecule. A molecule is the smallest particle of a substance. The smallest particle of a substance that can exist alone. That means with that, we can conclude that atom cannot stand alone. Atom cannot exist alone. But when atom is in form of a molecule, then it can exist alone. That is the smallest particle of a substance. That means the smallest substance. The smallest way a substance can able to exist, that can able to exist, is what we call what? A molecule. For example, hydrogen like this cannot exist alone. You can't just write H. You can't say any chemical equation where the writing H plus O is wrong. Because this hydrogen cannot stand alone. It cannot exist alone unless it's in the molecule form. So, if now to write a molecule of hydrogen now, let me say this let me write element and the molecule. So for example, hydrogen now. The molecule of hydrogen is H2. So if we want to write hydrogen to exist alone, we have to write the form of H2. That is why the chemical equation you can see them writing H2 plus O2. Why? Because they are in a molecule form. The molecule, one molecule of hydrogen is what? H2. That is how it can exist. That means if I write H in the chemical equation is wrong. Because an atom cannot exist alone. Although we have some exception of some atom that can exist alone. That the same, we have some exception like that. So for example, if I write neon, if I write sulfur, normally the molecule of sulfur is S8. But I can also write as S. For sulfur now, if I write S plus O2, we can stand alone. We have to let we have some exception of some atom that they have the same formula for atom, they also have the same formula for molecule. Sulfur, I can write the molecule of sulfur to be S8, and I can also write it as S. Neon, the molecule of neon is CNE, the atom is CNE, and the reason is because I explained was what we meant by shell the other time I think the first class. No, I think it's the last class or the second class. Where I say that where I draw some shells. For neon now, neon has a complete shell. 1, 2, 3, 4, 5, 6, 7, 8. It's complete. So what happens to neon is that neon cannot lose, it cannot gain. So neon normally is not reactive. Because what makes all these elements reactive is when they can lose electron or they can gain electron. But for neon, it has all the electrons filled up already. It can't lose, it can't gain. Because this outermost atmosphere have already complete 8. And I tell you that the maximum an outermost shell can complete is what? Is 8. And for neon here, all the electron is completely filled 8. That means it cannot lose, it cannot gain. So elements like neon, they are not reactive. So they cannot take part in the chemical reaction. That is why their atom is still the same thing as their molecule. Because they cannot react. They cannot partake in the chemical reaction. You can't say chemical reaction they are writing Ne plus Cl. It's not possible. You can't see Ne in the chemical reaction because it will not react. Because all the electron is filled up. So their reactivity depends on their what? The number of electrons in the what? In their atmosphere. If the number of electrons is complete, they cannot react. Like ozone. The molecule of ozone is what? O3. Oxygen. The molecule of oxygen is what? O2. So oxygen cannot stand alone unless it's in the form of what? O2 or O3. That is a molecule. So molecules are the smaller part of a substance. That means the smallest where a substance can be. For hydrogen now, there's not like H like this. We have hydrogen gas, which is H2. That means this hydrogen gas is a substance. That means, when you're talking about a molecule, it's the smallest particle of a substance. That means the smallest way a substance can exist. The smallest way a hydrogen can exist is what? H2. Like this is a molecule. That is a gas, H2. But H, that's not, this ordinary H is might not able to exist alone. But when we have H2, it's a gas. So it's a substance. So anywhere, anywhere you can write a substance is what? Is a molecule. Now, we have what we call atomicity. We have what we call atomicity. I'm trying to build a foundation so that we understand what I will talk about. That is why I moved to atom, molecule, and atomicity. What do we mean by atomicity? Atomicity is the number of atoms in one molecule. Is the number of atoms in what? In one molecule. For example, if I write a molecule like H2. So what is the atomicity of this H2? How many hydrogen, how many atoms is in this H2? We have got 2 hydrogen there. That means we have 2 atoms. So the atomicity is 2. If I write O3, what is the atomicity of this one? That means how many oxygen is here? 3. So the atomicity is 3. If I write He, how many atoms is in this He? 1. So the atomicity is 1. If I write P4, how many atoms is in this phosphorus? 4. So the atomicity is 4. And so on and so forth. So that is what we mean by atomicity. Atomicity is the number of atoms in a molecule. So since we have established that, then we can now move further to relative molecular mass. I want us to first understand what a molecule is before explaining relative molecular mass. That is why I first go into molecule. That is why I first explain what a molecule is for us. Because when I talk about the relative molecular mass, we are talking about a molecule, the mass of a molecule. Relative atomic mass, we are talking about the mass of an atom. You can see when I'm defining relative atomic mass, I say it's the number of times the average mass of one atom of the element. That means talking about relative molecular mass is talking about an atom. But the same way I define the relative atomic mass is the same way I will define the relative molecular mass. So relative molecular mass is what? The number of times the average mass of one molecule. You know, you understand, you remember, when I'm defining relative atomic mass, I say it's the number of times the average mass of one atom. But this one is the average mass of one molecule of a substance is heavier than 1/12 of carbon 12. Is heavier than 1/12 of carbon 12. So talking about a relative molecular mass, we are talking about the molecule. But talking about the relative atomic mass, we are talking about what? An atom. Let's now see some example. I write the formula for different molecules for us the other time. I think on the last class. But let me do a revision on that. I name different compounds for us. For example, Na2SO4. I name it for us. I know that someone can even name it from there, from you, at least in the last class. You have to understand that. We have said that this one is what? Sodium, tetra, oxo, sulfate. Then look for the rotation number. That will get 6. So sodium, tetra, oxo, sulfate, 6. So now if I now calculate the relative molecular mass, how will I calculate the relative molecular mass? Before I can calculate the relative molecular mass, we must first know the relative atomic mass. Now, what is the relative atomic mass of sodium? If you remember the table I drew for you, where I talked about the relative atomic mass of each element. For sodium, we remember that it's 23. So how many sodium is here? 2 sodium. So that is 2 times what? 23 plus. For sulfur, what is the relative atomic mass of sulfur? We'll write it the other time. It is what? 32 plus. How many oxygen is here? 4 oxygen. So that means 4 times. What is the relative atomic mass of oxygen? 16. Then let's now calculate. 2 times 23 is what? 46 plus 32 plus 4 times 16 is what? 64. Then we have what? 46 plus 64 is what? 78. 78 plus 64 is what? 132. 142. That is 142. Unit is gram per mole. That is 78 plus. That is 142. So that is what? Gram per mole. You can see how you get the relative molecular mass. Very easy. Let's do another one. Let's get the relative molecular mass of limestone. Who can tell me the formula for limestone? The formula for limestone is CaCO3. This is formula for limestone. So what are the relative molecular mass? Calcium is what? 40. Carbon is what? 12. How many oxygen is here? 3. What is the mass of oxygen? 16. Then we have what? 40 plus 12 plus 48. 48 plus 12 is what? 60. 60 plus 40 is what? 100. That is 100 gram per mole. That is the relative molecular mass of limestone. Let's check for global source. The formula for global salt is Na2SO4.10H2O. This is global salt. And I don't think I explained when we have 10H2O for you in the other class. Where I explained how to name the compound. Let me tell you about that. At least I tell you how you can know this one. So let me, if now does 10H2O, whenever I see H2O in the compound, they call it hydrate. Whenever I see H2O in the compound, they call it hydrate. So, and if you remember, I told you that 2 means di, 3 means tri, 4 means tetra, 5 means penta, 6 means hexa, 7 means hepta, 8 means octa, 9 means nona, and 10 means deca. So what is here 10? 10 is what? Deca, from a decagon. If you remember your mathematics, when you have a pentagon, hexagon, tetragon, octagon, nonagon, decagon. So 10 is what? Deca. So whenever I see 10 here, what does it mean? Deca. So if I have to name it, what is the name? Sodium, tetra, oxo, sulfate, 6. And now, what is this 10? Deca. H2O is what? Hydrate. Hydrate. So this is what? Sodium, tetra, oxo, sulfate, 6, decahydrate. That is the formula of what? Na2SO4 plus 10H2O. So let's now calculate the relative molecular mass of that compound. What about the relative molecular mass? Now let's try. D is what? 2 bracket 23 plus 32 plus 4 bracket 16 plus now 10 brackets. There's 10 here. Plus 10 bracket. Hydrogen is what? We have how many hydrogen there? 2 hydrogen. Then the molecular mass of hydrogen is what? 1. Plus oxygen is what? 16. Then we now have what? 46 plus 32 plus 64 plus 10 bracket 18. Then we have it to be what? 46 plus 32 is what? 70. That is what? 142 plus 180. And that gives us what? 332 grams per mole. We have 46 plus 32 plus 64. That is 142. 10 times 18 is what? 180. 142 plus 180. That gives us what? 322 grams per mole. So that's how we get the relative molecular mass of what? Of our global source. Let me give one more example. Then we move away from the relative molecular mass. Let me give you an example of slake lime. Slake lime. The formula for slake lime is Ca bracket OH bracket 2. And what is the calcium is what? 40 plus bracket oxygen 16, hydrogen 1 times, we have 2 of them, 2. And that gives us 40 plus 70 times 2. And that gives us 40 plus 34. And that gives 74 grams per mole. So that is how we get the relative molecular mass of slake lime. So from here, there are some questions you might be told to calculate the percentage by mass. So I also move to the percentage by mass, then we stop it there for today. Now, some question might require you to calculate the percentage by mass. For example, calculate the percentage by mass of nitrogen in trioxonitrate 5 acid. So this is a question. Calculate the percentage by mass of nitrogen in trioxonitrate 5 acid. Firstly, if it is me that said the question, I won't give the formula for this trioxonitrate 5 acid because I expect you to know it. Let's write the name. If you remember, I told you that trioxo means what? O3. Nitrate is what? Nitrogen. And whenever I say acid, it's H. So if now we have that means we have what? Acid is hydrogen. Trioxonitrate 5 acid is a radical, NO3. That is how we now form the compound with this. Normally you know that NO3, when we write the radicals the other time, is NO3 minus. And I tell you that the charge on nitrogen is what? H plus. How will we now form the compound with this? 1, 1. Because this is minus 1, this one is plus 1. And I tell you that I'm not putting the charge. Instead of not putting all this charge there. You do not need. So I will not put this minus 1, I will not put plus 1. What will have the formula? I say we cross multiply. H times 1, H, NO3 times 1, NO3. That is how you have what? HNO3. That means the formula for trioxonitrate 5 acid is HNO3. So let us now calculate the percentage by mass of nitrogen. Where is nitrogen? N in what? HNO3. Where, let's see. That means nitrogen over HNO3 times 100. What's the molar mass of nitrogen? 14. What's the molar mass of hydrogen? 1 plus nitrogen 14 plus oxygen is what? 3 brackets How many oxygen? 16 times 100. And that gives 14 over 150 plus 48 times 100. Then we have 14 over 63 times 100. And that should give us 22.2%. So that is what? Percentage of what? Of nitrogen. Percentage of nitrogen in what? In HNO3. So that is how to calculate the percentage by mass. That is how to calculate the percentage by mass. Let me give us the last example under the percentage by mass. If you are told to calculate the percentage by mass of, let me say, carbon in soda ash, the formula for the name of soda ash is sodium trioxocarbonate 4. So in this case, we are calculating the percentage of carbon. So what is the formula for sodium trioxocarbonate 4? I only tell you how you can form a compound with it. Sodium is what? Na. Trioxocarbonate 4 is what? CO3. And I told you that this is a radical. And this radical carry what? 2 minus. And we established in the last class that N is what? Na plus. So how we now form a compound with it? Plus 1 is 1, minus 2 is what? 2. Plus multiply. What will have the formula? Na times 2, Na2. CO3 times 1, CO3. So the formula of sodium trioxocarbonate 4 is Na to CO3. So now we calculate the percentage of carbon. What will be the percentage of carbon? That is carbon over Na2CO3 times 100. What is the numbers of carbon? Okay, 12 over 2 times 23 plus 12 plus 3 bracket 16 times 100. And that gives us 12 over 106 times 100. And what would that now give us? If you calculate it better, it will give us 11.5%. That will be the percentage of carbon in soda ash. Okay, if you have to calculate the percentage of oxygen in this, there is the reason why I want to calculate the percentage of oxygen, because I've not treated something that's somewhat similar to that. Percentage of oxygen in NaCO3. Each percentage of oxygen, how you calculate it? Percentage of oxygen in NaCO3. How many oxygen do you have in NaCO3? 3 oxygen. That means 3 bracket oxygen over Na to CO3 times 100. That percentage of oxygen will now give us 3 bracket 16 over 106 times 100. And that gives us 48 over 106 times 100. And that should give us 45%. So you can see that means the number of oxygen in NaCO3. That will determine the number of oxygen we write in the fraction. The reason why we write just ordinary 1 carbon here is because we have only 1 carbon in the compound. So we will stop here for today. Thank you for watching, and if you have any question, don't hesitate to comment and subscribe. Please, that is very important. Thank you so much.